Alright, so in this problem, we were given a flight route on the sphere, which was supposed to model Earth. The flight route consisted of spherical arc segments like this one from point P1 to P2, and maybe onwards to P3, P4, and so on. And on the Earth, there are also continents. Here is an example of a continent from Q1 to Q2, over to this point, to that point, to that point, and back to Q1. So these segments are also spherical arc segments. And the goal now was to compute how large a fraction of this route goes over water. And so, in general, what we have to do then is to find the intersections of the route. So we can deal with each route segment separately. So let's do the one from P1 to P2. So we then find all intersections between this route segment and all of the continents. So in this case, we would like to find these two intersections. And then once we found those, the problem was so nice that there are basically no special cases. You could worry about what happens if the route goes exactly through a vertex, or if it goes parallel to the beach of a continent, or something like this. But this was all ruled out in the problem statement. So the only thing we have to worry about are these. So nothing special happens. We only have to care about these intersections. So once we found those intersections, we're basically done, because now we can sort these by the distance from the first point. So then we know that first there's a stretch from P1 to this first intersection point, where we're over water, in this case. And then there's a stretch from the first intersection point to the second one, where we're over land, and then so on. Next stretch would be over water. And in the problem statement, it was guaranteed that the very first point of the first part of the route was over land. So we knew from the initial point whether we were over land or water, and then one can just keep track of this as we go. So it only boils down to this task of finding these intersection points between two spherical arc segments, P1, P2 and Q1, Q2. So the thing to observe here is that the great circle of this arc, P1, P2, it's defined by the equation that it's the set of points that are orthogonal to the normal P1 cross P2. This is the cross product of P1 and P2. So the set of points on this spherical arc are the unit vectors that are orthogonal to P1 cross P2. So now we're interested in the points that are the intersection point. It should be on both great circles, the great circle defined by P1, P2, and the great circle defined by Q1, Q2. So in other words, the point R should be orthogonal to both P1 cross P2 and to Q1 cross Q2. But there are only two such points, and they are the cross product of these normals. So it's the P1 cross P2 cross Q1 cross Q2. And plus minus, and then you have to normalize by the length of this thing to get the unit vector. And then it's either that or the negation of that. So then you get two basically possibilities for the intersection point between these two line segments. And then you have to check if either of these two candidates is actually an intersection, or whether somehow you only know that this point lies on the two great circles, but maybe they're outside the line segments. And this you can simply check by checking the distance, checking the triangle inequality holds with equality. So you check the distance from P1 to your point R, and then from R to P2, and the sum of these two distances should be the distance from P1 to P2. And here distances are measured by angle. And yeah, that's basically it.